Hello, DevOps. How are you doing out there? Now, you've got to realize, I have been asking that question to a webcam for a year. And I've said, how are you doing out there? And in my head, lots of people have gone, yay, but I can't hear them. How are you doing out there? Yay. See? It's beautiful. We have duplex communication going on. Hello, and thank you for coming to a talk about plain text. Hands up who loves text. Hands up who hates text. Hands up who's like text. I don't really have an opinion about text. I'm a developer. I live in text. It's like saying to fish, hey, what do you think about the water? And fish like, water? Oh, that stuff. Oh, yeah, I never really thought about it very much. So yeah, I am going to talk to you about plain text and why it doesn't really exist. My name is Beattie. I run a company called ASCII, based here in London, that does software training and strategy consultancy. So if you need software training or strategy consultancy, come and talk to me afterwards. Microsoft MVP with the Developer Tech program. Go and check out Microsoft on the stand there. Not only do I like them very much, they're doing some very cool stuff with Java and Azure at the moment. I run a .NET user group. It's okay. I know this is a Java crowd. I speak a little Java. We're going to be fine. And I once invented a programming language as a joke that's now a joke with a reference implementation and a formal test suite. And if you want to hear the story of Rockstar, come to the Art of Code at the end of the day in the main gallery hall, and you can hear all about that. And yes, this is a talk about plain text. And the thing about technology and computers and software and all the stuff we do is that what makes it useful is that we can take an idea, something that exists in the real world or in our heads, a piece of music, a sentence, a phrase, a picture of something, and we can turn that into technology, and then we can say to the technology, hey, search this, index this, send this to Australia, do something cool with this, and when it comes out at the other end, another human being can share that idea that we had. And this is true of all kinds of things, and it is true of text. Human beings invented writing about probably 5,000 years ago. We're not exactly sure. But writing didn't get exciting until about 150 years ago when we thought, hey, what if we mix writing and electricity and we invent the telegraph system? Now this, I think, is the earliest text encoding system that was ever used anywhere in the world. There's a thing called a Cook and Wheatstone telegraph. Now this was used on railway networks here in the UK in about the 1820s, 1830s, and it used 5 cables. Now, the thing you've got to realize about early telegraph system, there is no way of saying to the person on the other end, hey, we're about to send you a telegraph message, because we haven't invented that technology yet. So they ran 5 cables, which were about 15 miles, about 20 kilometers long, between Paddington railway station here in London and a town called West Drayton. And when they wanted to send a message, what they had to do, you see these 5 needles across the middle of the dial here. They would connect 2 of those cables into a circuit, and what that circuit would do is it would make one needle deflect in one direction and the other one in another direction, and you would read off on the dial where they crossed, and that's how you read it. Cook was a business person. The Cook and Wheatstone system was created by 2 people, kind of a precursor to a lot of the stuff we deal with at work every day. Cook was a business person. He said the system had to be trivially easy to use. You don't have to read the manual, and it should be really expensive. Wheatstone was a scientist. He said, no, we should give this technology away for free, and it's okay if people have to work a little bit to send messages in real time over hundreds of kilometers of distance. And they fought, and this is the compromise they came up with. It's supposed to be nice and easy to use, the first intuitive user interface. But anytime you're, bashing your head against issues with text encoding, just take a moment to think, we could have ended up with a 5-symbol trinary encoding system that only supported 24 letters of the alphabet, because if you wanted to encode D in the telegraph system, the code wasn't 1s and 0s, it was neutral plus, neutral, neutral, minus. So I think we dodged a little bit of a bullet there on the whole encoding system. Now the 5-wire telegraph system had a problem. Wires break, especially when they're 15 miles long and you've run them through the damp English countryside. Eventually, one of the wires stopped working, and they went, well, we could run another wire, or we could invent a 4-cable telegraph system, which they did. And then another wire stopped working, and they went, well, with the 4, could we do 3? Meanwhile, across the other side of the US, a guy called Samuel Morse is working on this, which you might recognize. Because Samuel Morse is like, we need a single-wire telegraph encoding system. We need a way of sending information as text using just 1 wire. Not even 2 wires, Because ground in a Morse code system is actually the ground. It is literally a difference between this piece of wire and the ground underneath your feet. Now, Morse invented the encoding system. This is International Morse code. This is not actually the one he invented. It's named after him because it was kind of his idea. This system, which we still use today, was created by a German engineer called Friedrich Gerke. And in 1865, they had a conference in Paris, the International Telecommunications Congress, which seems a little ambitious because they'd only just invented international telecommunications. And they decided that International Morse code was the standard that everyone was going to use. And within a decade, this was everywhere, because this is when they were rolling out telegraph systems across the world. And if you've ever worked on any software system, you'll know that when you have no users, you can do anything you like. Change it, refactor it, modify it, remove that button. As soon as people are using your system, you're not allowed to change your mind anymore because it'll upset your users. And so Morse code was basically set in stone. Once these telegraph networks were installed, it was almost inconceivable that something was going to topple Morse code. And it lasted 100 years. Almost exactly 100 years. 1965, something finally happened that made them think we need a better system. And it was this, our friend the digital computer. And computers don't cope well with Morse code because Morse code is actually a time-based encoding system. The dots and dashes, you need a clock because you need to know, beep, was that a very long dot or a very short dash? Doot, 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 doot. So you need some kind of clock. Computers don't cope well with time-based information. We needed something that was effectively temporally stateless. Now, ASCII, the American Standard Code for Information Interchange, was ratified in 1965, exactly a century after Morse code. And that's pretty much the same ASCII we still use today. And the thing you've got to realize about ASCII is that it was created to run on these mechanical teleprinters with no screens that got data from punch cards. So when you look at ASCII, ASCII looks like this. And a lot of us, we work with this stuff all day, every day, and probably never stop to think that once upon a time, somebody had to sit down and design ASCII and make all kinds of decisions about how this encoding system was going to work. Now, if we start at the beginning here, ASCII 0, any of you worked with C or C++, ASCII 0 is the null character, which we still use today as, hey, you've run out of string. And if you just keep on going, you've just invented the buffer overflow error. Congratulations, you can go and hack stuff with that now. ASCII code 1 was the start of heading. Now, when you had a mechanical teleprinter, you had to use these things a lot, so they gave them all shortcut keys. If you wanted to send the start of heading control code to your teleprinter, you pressed Control A. If you wanted to send start of text, you pressed Control B. If your teleprinter was going crazy and printing stuff and you were like, no, stop, you would send Control C, end of text. And that one survives. And to this day, if your computer is printing a whole bunch of stuff you don't want to be printing, Control C is what you go for. Now, Control D, end of transmission, inquiry, acknowledgement, we don't use those very often. Control G, which is the bell character. If you open a Windows terminal and you type echo space, hold Control, press G, and press Enter, your computer will go ping, because that's the modern equivalent of ringing a bell that's attached to your old clunky mechanical computer there. And then we get into the fun block. We get into backspaces and horizontal tabs and line feeds. And by the way, ASCII code 1011 there, that's vertical tab. Anyone ever says tabs versus spaces? Tell them you use vertical tabs. It'll end the conversation real quick. Now, why a carriage return and new line? Why are we still having these debates about how to end a line? Well, a mechanical teleprinter works like this. It has a carriage, and when you get to the end of the line, you need to return the carriage to where it came from, and then you need to feed the next line through your printer. And it turns out these things couldn't do text formatting, but they could fake bold, because you could print the same line twice by doing a carriage return and then printing it again, and that overprint would give you this kind of pseudo-bold effect. So there was a valid application for a carriage return that didn't have a line feed immediately after it. Now, these are decades later. We are still having these discussions about carriage return line feed versus carriage return versus line feed. And it basically polarizes. If you're on a system that evolved from Linux or Android or something like that, you just use new line. If you're on a Windows system, you use a carriage return new line. Reason is, Linux evolved out of Unix. Unix evolved out of Multics. Multics was the first operating system that had device drivers. It had a little piece of code that sat between the operating system and the teleprinter, and that piece of code said, hey, when they send us a new line, do the carriage return as well. Otherwise, the printer's just going to go off to the right and fall off the end. Whereas Windows evolved out of Windows, evolved out of Windows, evolved out of DOS, evolved out of CP/M, which was designed to run on the cheapest computers possible, and so it did not have device driver support, so you had to send a return and a new line. And so every time you get a file encoding problem switching from Linux to Windows and back, that's what you're doing. You're dealing with the fact that Multics had device drivers and the original CP/M mini computers didn't. Now, the next chunk of ASCII, we have the decimal digits. And something computers do a lot is they turn numbers into text and back again. And this is quite clever, because the way that they do this is they just say chop off the big half, and what's left will be the binary representation of the number represented by that digit. And this is a 4-bit operation. Even the simplest computers imaginable can do this natively in the registers really, really fast. The alphanumeric block, we have the ASCII capital and the ASCII lowercase letters. Now, you ever wonder why ASCII capital A is 65 and lowercase a is 97? It's because they are separated by 1 bit. If you want to do a case-insensitive string comparison in ASCII, you switch off bit number 6, and then uppercase and lowercase are the same, and you can do a very, very fast case-insensitive sort, search, all these kinds of operations. Then finally, we got a whole bunch of punctuation and stuff crops up in here, and right at the bottom of the block, ASCII 127 is del, the delete character. The reason that ASCII 127 is delete is that in binary, it looks like this. And if you want to erase information that has been punched into a card, you can't fill the holes back in. All you can do is punch out all the rest of the holes so that the card is no longer readable. So that's ASCII delete, top of the basic 7-bit ASCII block. And America turns around and it goes, hey, good job, everyone. We solved text encoding. And the rest of the world goes, sorry, you did what? Like, we can't work with this. Some countries are like, this is literally like there is not a single part of our alphabet in the solution that you just delivered. Other countries are like, well, we could kind of work with this. Now, I grew up in Zimbabwe, where I grew up speaking English and working with dollars and cents. My first experience of text encoding was this fellow here, the British pound sign. Because when I moved to the UK in about 1988, I wanted to print some homework, and I couldn't, because I couldn't print my pound sign because my computer and my printer could not agree on what a pound sign was supposed to look like, because the Americans hadn't solved that problem back in 1965, because Americans in 1965 didn't use pound signs for anything. They used dollars for everything. And the solution to this, a whole bunch of people, companies, organizations, they look at ASCII and they're like, hang on, we've got 8 bits in a byte, and ASCII's a 7-bit encoding system. Is anyone using this bit? And of course, nobody says, hands off, that's ours, because the Americans are happy and no one else is really dealing with very much of this. And so a whole lot of companies all around the same time go, we've got a good idea. We're going to use the top half of ASCII for our own thing. Now, one of the most famous implementations of this, does this look familiar to anyone? We got any developers of a certain age in here? This is the code page that shipped with the IBM PC. And they said, all right, you've got ASCII is the top half of this chart. The bottom half, we're going to add stuff we think is useful. So they added characters for most Western European languages. So Swedish, Danish, Norwegian, French, these kinds of languages are all working. They added some box drawing characters, so you could do little menus. They added half of the Greek alphabet. Anyone know why half? They didn't care about Greek, they cared about physics. So they included the letters of the Greek alphabet that are used in science and mathematics, but not the letters of the Greek alphabet that are used to talk to people who can read Greek, right? Because they were pushed for space. You know, every single one of these, you put that in, you've got to take another one out to make space for it. But then they went, well, why don't we reuse the bottom block of ASCII for things like playing card symbols so we can write games. And if you've ever seen an IBM PC crash really hard, what you get is a screen full of little smiley faces and playing cards, because those are teletype control codes being interpreted in this code page, because the operating system is trying to stop the runaway printer. And the computer's going, yeah, I can print control code 11. Look, there it is, little smiley face. Thank you for crashing with IBM today. Now, anyone recognize this alphabet? This is the Cyrillic alphabet. One of the big civilizations that was like, we can't work with ASCII was the Soviet Union, Russia, Ukraine, all the countries that use the Slavic alphabets and the Cyrillic alphabet system. And there was an international standard for encoding Russian in extended ASCII, which was created by ISO, the International Standards Organization. And basically they said, oh, here's a bunch of code points for it. Now the problem was, and in some cases still is, some systems think the 8th bit doesn't matter, and they will chop it off. Some word processors would use the 8th bit for internal housekeeping. Some email systems will strip off the 8th bit because they think email headers only use 7-bit ASCII. And if you chop the top bit of, does anyone know what this says, by the way? Anyone here read Russian? It says privyet. It means hello, hi. Now, if you chop off the top bit and then try and turn this back into ASCII, what you get out is nonsense, completely unreadable. And so the Russians went, well, we've got a good idea. We're going to invent our own encoding system. We are going to invent the Code Obnema Informacja 8-bit, KOI-8. And KOI-8 is a brilliant hack, because what they did is they took the letters of the Russian alphabet, they assigned them these code points, and if you drop the top bit off one of those, what you get back out is slightly mangled English that reads out loud like the Russian it was supposed to be, but with the upper and lowercase characters reversed. So if you get an email from someone that says privyet, you're like, I know this is Russian, I know it's been corrupted, and I can still see what it was supposed to say in the first place, which I just think is absolutely genius. Now, this kind of stuff, it's easy to think, oh yeah, this is stuff that used to happen. It doesn't really happen anymore. I found a story. I did a version of this talk in an event, and afterwards someone came up and said, do you know about the parcel that was sent to Russia? And I was like, no, tell me the story. And they said, so this, I fictionalized the details I couldn't find. But this is around 2002. There's a woman in France who has an email pen friend in Russia, and they're both big Harry Potter fans. And Svetlana sends an email to Claudette saying, yeah, please, that would be amazing. Send me the new Harry Potter book, because we can't get it yet in Russia. Here's my address. It's in the Russian alphabet, so please copy it down very carefully. And it's this address, Moscow, Venetskogo 37, Pretnovoye Svetlana. Thanks, Sveta. Now, this is sent using the KOI-8 code page, but what Claudette gets is that, which is in the Western European ISO 8859-1 code page, and she follows the instructions. She very carefully, you can see here the two code pages, and it's the same underlying values. But what Claudette does is she very carefully copies out the Russian alphabet onto the envelope and posts it. And somebody in the Russian Postal Service recognizes this and goes, I know what this means, and fills in the actual Russian letters that it was supposed to be, and the book got there. This is the Harry Potter book 2002 actually arrived in Russia thanks to a Russian post office worker who knew how to solve text encoding problems with a red biro. There's one other wonderful example of the whole ASCII versus Russian encoding thing that crops up. In 1987, Billy Joel played a concert in Leningrad, and they released it. It was one of the first Western musicians to release an album in the Soviet Union, and it was called Concert. And on the album cover, they spelled the word concert in Russian using the Cyrillic alphabet. And then someone went, I need to put this in my music database, K-O-H-U-E-P-T, K-O-H-U-E-P-T. And that just kind of got baked into the databases that drive record companies. And so when we got Spotify, and when we got iTunes Music and all this kind of stuff, if you go on iTunes right now, you can buy Kohuept Live in Leningrad by Billy Joel, because it's stuck now and we can't change it back. And so that's just what the record is called. Now, like I said, a lot of people came along and went, oh, code pages, yeah, we'll invent those. This is the number of code pages that are on Wikipedia right now, because IBM invented one for, there's IBM Bulgarian, and there's also Apple Bulgarian, and there's PostScript Bulgarian, and there's IBM Ebkadik Bulgarian, and Hebrew, and Korean, all these different things. It was chaos. Now, for a long time, we kind of managed the chaos, but then when the World Wide Web and email kind of broke into the mainstream, we needed computers that could talk to each other. More importantly, the people behind those computers needed to be able to talk to each other. And so we needed a unified encoding system, Unicode. Now, the Unicode Consortium was started in the project started in 88. They sort of established the foundation in 1991. And their mission statement is this: to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Now, that's a hell of a mission statement. And the astonishing thing is they did it. Now, you break that down a little bit. First of all, let's start at the end. All computers and devices. Well, if you want everyone to use your thing, you make it good, you make it easy to implement, you make it the best solution possible, and you make it free. They tick, 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 tick. They did all those things. And so Unicode is a standard that is out there that anybody can implement on any platform based on these really good specifications about how it all works. Every letter and symbol needed for all human languages, including ancient Sumerian, English, Egyptian hieroglyphics, languages that aren't used anymore because archaeologists, historical researchers, they need to be able to send emails with their research as well. So what's a single consistent way to represent each letter and symbol? Well, here's a pair of strings. Are they the same? Hands up if you think they're the same. Hands up if you think they look the same. They look the same. They're not the same. The top one is the first half of the Russian word horosho. The bottom one is the middle of the English word exoplanet. Now, that probably means they're the same shape. They are different sounds. They are different alphabets. They're different letters, even though they are the same shape. This is the kind of problems that Unicode started dealing with. But then we get into things like this. Now, that second letter there, this is the Norwegian word hårfjerner. It means hairdryer. And I can't read Norwegian, but I can read English, so when I look at this, my English-British brain goes, oh, it's got extra bits, I'll ignore them. I'll get a half-owner instead. And the Norwegians roll around laughing, because that's not how you say hairdryer. And this, is that a A with an extra bit that we can ignore it? Is it a different letter of the alphabet, Now, this sounds like a kind of academic thing. It actually becomes a pretty big deal. Let's take a look at an English sentence. So we're going to meet some friends of mine. This is François Borda, who's a French archaeologist. And this is Motley Crue, the rock band from Los Angeles. And François, the archaeologist, went to the Motley Crue concert. Now, this is written in English, but there are 4 characters in this sentence which are not part of the English alphabet. So what do we do about them? How do we encode these? Do we borrow them from somewhere? Do we combine them? Now, Motley Crue looking stupid, not a big deal. They looked stupid anyway. But this can have real consequences. This is Magnus Martensson. Actually, no, this is not Magnus Martensson. This is Magnus Mortensson. Magnus is a Swedish developer. He's a Microsoft Azure MVP. A couple of years back, Magnus is flying to the US to go to a software conference. And he gets into some trouble. Now, Magnus has a Swedish passport. And the second letter of his surname is the letter O, which does not exist in English. It is the 28th letter of the Swedish alphabet, and it is the letter O. It is not an A with a circle, it is an O. Now, the Swedish government, there is a strip at the bottom of your passport here which has to be in 7-bit ASCII. And the Swedish government says that to turn O into ASCII, you double it up, AA. The people who printed Magnus' airline ticket, they didn't care about the Swedish government. They just like, well, it's an A, we'll take the circle off and that's fine. And so Magnus gets to United States Border Control with a ticket that doesn't match the name on his passport. And the US border officials, of course, are famously understanding and up to speed on text encoding problems. He had to answer some. Now, he's a well-dressed, polite white guy on his way to see Microsoft. He didn't have too much difficulty. Imagine how that might have played out if he was somebody else, Now, we are just getting warmed up. Let's take a look at a list of European cities. We have Berlin, we have Aachen, we have Zurich, we have Aarhus, and we have Örebro. And we are going to put these in a database. We are using Microsoft SQL Server here. We're going to declare a table called cities. We're going to insert all those values, and we're going to select them back out. And there we go. We got a list of cities. Let's go and do a little query. Select star from cities where name equals Örebro. Hang on, but we just put that there. Maybe it's case sensitive. Nope, still nothing comes back. Okay, well, if Örebro equals Örebro, print yes, otherwise print no. No, what? Umlaut. Maybe those 2 little dots are making a difference here. Now, the computer is not going to decide for us. We need to tell it how to make decisions. We are going to say, if Örebro equals Örebro, according to the rules of the Latin General 1 case-insensitive, accent-insensitive collation, print yes, otherwise print no. Yes. According to this set of rules, it does. These are collations. A collation is a set of rules for saying, what does alphabetical order mean right here, right now, for the purpose of answering this question? Which strings are equivalent to other strings? Which strings are sorted before or sorted after other strings? Now, if we select star from cities ordered by name, we get Berlin, Aachen, Aarhus, Berlin, Örebro, Zurich. This is Latin sorting because it ignores the umlaut. It thinks is the same as an O. If we say do this using the Finnish and Swedish alphabetical order, we get this. Örebro is now at the end because in Swedish, comes after Z. It's at the 27th, 28th letter of the alphabet there. If we do the same thing using Danish and Norwegian collation, Berlin is the first city in our list. And then Zurich, and then Örebro, and then Aachen, and then Aarhus. Because the rules of Danish and Norwegian orthography say that AA, when you see them together, is the letter O, and that should be sorted at the end of the alphabet. Now, this is Denmark's second city, Aarhus. And in 1948, there was a thing called the Danish spelling reform. And they took AA, Aarhus, and they changed it for A with a circle, Aarhus. And it was like that from 1948 until 2011. Now, as part of the Danish spelling reform, they added these new letters to the Danish alphabet, and they made a rule that anything used to start with the AA is now spelt with one of those new letters, goes at the end of the alphabet, end of the phone book, end of the encyclopedia. In 2011, the people of Aarhus voted to change the spelling back. So it was easier to find on TripAdvisor and internet search engines, but they didn't change the position in the alphabet. So this list on the right-hand side is in correct alphabetical order according to Danish and Norwegian ethnography and cultural conventions. And if you show this to someone, we got anyone Danish or Norwegian in today? Yeah, does this make sense? Yes. Yeah, see? Obviously. Because Aachen is clearly not in Scandinavia, so it's A, but Aarhus is clearly in Scandinavia, so it's O, so it goes at the end, right? It's completely obvious. Unless you didn't grow up with that as a convention, you're thinking, how can you even get that right? And you can't. If you use Norwegian language Windows, aardvark appears at the end of the file explorer because R shows up at the end of the alphabet. If you do actually need to do this in a piece of software, what you need to do is cheat. You put in a column for the humans and a column for the computers, and if there's something in the computer column, it overrides the human column when it comes to sorting and collation and that kind of thing. So if you need to put Aachen in and it needs to be at the start of the list in a Norwegian or Danish collation, put in a little cheat name like this one here so that it knows what to sort it on. Now then, what all this goes to show. I've occasionally heard people go, oh, I'm not really interested in culture and politics and history. I just do computers. We are surrounded every day. The decisions we have to make to write a line of code without bugs in it require us to understand the cultural distinctions between Norway, Finland, Sweden, Denmark, Germany, World War II, the Danish spelling reform, the politics, the people of Aarhus voting to change their name back. There is no technology that does not exist without politics and culture and human influence, because that's where the problems came from that we have all been trying to solve and still are trying to solve. Let's try and just solve one letter. Let's try and solve the letter S with a cedilla, a little hook tail on the bottom. Now, this thing, it exists in Unicode as code point 00C7. It's got its own code. But Unicode also says, well, you can take a regular letter C, and you can put a little tail on it using something called a combining character, and that will give you the same shape that represents the same sound as part of the same alphabet, right? And you can stack these things. You can put combining characters on top of combining characters on top of combining characters on top of combining characters. And if you take this far enough, you can then go and copy and paste it onto an internet message board, and you end up with Zalgo text. But let's take a look at our friends Motley Crue, or Mötley Crüe, as they're called in Germany. Here's how you write Motley Crue using those code points, and here is another valid way of writing Motley Crue using combining diaresis characters. Are these strings equivalent? Are they? Well, binary equivalent, no. One of them is a different length, for starters. They can't be the same string. Again, what Unicode did is they said, we're not going to solve this problem for you. We're going to give you some solutions, and you need to tell us which one applies in this particular situation. Now, the way that you do this in Java is there is a thing called the text normalizer, which is in the java.txt package. And it defines 4 different normalization forms. And those are listed up here. There's the normalized form NFC. NFC here stands for composed. It means squash this thing down into the smallest number of code points. The D stands for decomposed, which is the opposite. Stretch this thing out into the largest number of code points. Take all the accents off and make them combining characters. And then the K in these two, that stands for what's called canonical, because C was already being used for something else. They got 3 letters into the acronym and then had a naming conflict. I love software. Now, what do these things actually mean? Well, let's take a Motley Crue here. So we've got Motley Crue at the top, and then we've got Motley Crue here, where we are adding the accents using a combining diaresis. We're going to run those through our normalization code here. Now, to get this to work, you've got to encode UTF-8. You've got to pass the encoding flag to the compiler. Then you run the thing, and it says, well, these strings are not equal, but they are considered equal under all 4 different forms of Unicode normalization. So, well, let's have a look at another one. Unicode also gives us plain text and plain text, where one of them, the letters are in little bubbles, because it looks pretty, because you can put it in your Twitter profile. Now, with these ones, it says, well, no, those are, first of all, they are not the same string, and they are not the same string unless you force them into a canonical form, where we will ignore decorations and typography, and we'll be like, look, is it a letter P, yes or no? Just, I don't care what it looks like, is it the letter P? And under a canonical form, the answer to that question is yes. Now, my personal experience with text encoding, like I said, it started with trying to print a pound sign in 1989 on a 286 PC. But the real turning point for me was when I got into work one morning, back 5 or 6 years ago, and someone came to my desk and said, dude, I think we've been hacked. Now, when you work in IT, this happens a lot. We've been hacked. No, you haven't. You've just right-clicked view source on Facebook again, Mum. I told you to stop doing that. But on this occasion, the person who said, I think we've been hacked, was a very, very good security engineer. I'm like, why do you think we've been hacked? There's Chinese in the Windows event logs. I'm like, no. And we open the Windows event logs, and there is Chinese in the Windows event logs. So I do what good managers do. I say, right, you check the logs, see if there's any, if this stuff is showing up anywhere else. When did it start? When did it stop? You go and search the databases, see if there's any of this actually in the tables anywhere. You check the firewall, see if there's anything suspicious. You go and tell the business that we might have an incident. We'll update them in 15 minutes. I'm going to put my feet up, and I'm going to post about it on Twitter, because when you've delegated all the important work, that's what you do. And Twitter got back faster than any of the people, with someone going, oops, that looks like a Unicode mapping error. And then the fake Unicode account, which I love, said, yeah, the low bits are all null, so this is probably UTF-16 LE being mistaken for UTF-16 Beattie. And I'm going, I should probably find out really quickly what all these words mean, because this might be important. So I dive headfirst into everything I can find about Unicode and do like half an hour of really intensive kind of research on it and figure out what's going on. Now, the word delete, which shows up a lot in database logs, because you delete things from databases, internally on Windows and on Java and JavaScript and Android, everything is represented using 2 bytes, because that kind of gives you enough space for most letters in most alphabets, but it's still relatively performant. So every letter gets 2 bytes of space. And this is how it's managed internally. This is what actually gets allocated in memory. Now, if you get those bytes the wrong way round, what you get at the other end is the word delete turns into this little string of Chinese, which doesn't really mean anything. It's the character chi, climb, Jan, climb something, climb. I'm like, if this is a ransom note, I don't know what they're after. It's probably not hackers. It's probably a systems problem here. So next question, why has the Windows event log switched from being big endian to little endian? Well, it hadn't. What had happened is a network switch in our data center had got a bit of a headache in the night, and it was dropping 1 byte from the data stream about every 3 minutes. So every 3 minutes, we'd lose 1 byte, and everything else would just get shuffled up, and we'd get this. And everything would switch across, and it would be in Chinese for 3 minutes, and then after 3 minutes, it would drop another byte, everything would shuffle over, and it would go back to making sense. Now, this is kind of a pitfall of UTF-16, is you need to know which way round it is, because otherwise it doesn't make any sense. If you read it the wrong way, you get the wrong letters in the wrong alphabets. Also, you know the ROT13, like the Caesar cipher? There's a thing called ROT65535, which turns English into Chinese nonsense and back again, which is quite good for steganography if you want a very kind of low-tech solution for encoding stuff. But let's talk about encoding systems. Now, UTF-16, you look at this. This is very, very inefficient. All of those ASCII letters at the top, half of that memory is being used to store zeros, which, on an operating system, no big deal. Speed is more important than bandwidth, because we want to be able to know how long strings are and how much memory to allocate for a certain number of characters. When you get out onto the web, often you get to a point where bandwidth is more important than speed, and the volume of traffic becomes a serious consideration. Now, here's a web page. Really simple web page. This is Ukrainian. This just says Privyet in Ukrainian. And if we encode this in UTF-16, it looks like this. That's the bit we need. That's the bit that actually you can't do in ASCII, because HTML is made out of ASCII, and CSS and JavaScript and all the languages, the metadata, the angle brackets, that's all ASCII. So if you turn the whole thing into UTF-16, all of this space is wasted, and 44% of your network traffic is sending zeros backwards and forwards. And you have to send them, because the thing on the other end can't just be like, I'll just put zeros in wherever I think there's a gap, because that's not going to work. So we needed a more efficient encoding system. And this, I think, is one of the most brilliant things that the Unicode consortium came up with, one of the most fantastic hacks in history. They created a thing called UTF-8. Now, the first rule of UTF-8 is anything that starts with a 0, any byte starts with a 0, the remaining 7 bits are ASCII, same as it was in 1965. No change to that. So all the old ASCII documents that are floating around on the web and FTP servers and Gopher and email archives, those are valid UTF-8 just because they were valid ASCII in the first place and they didn't break anything. Any byte that starts with a 1 is part of a multi-byte encoding sequence. And if you are scanning through a UTF-8 string and you find a 10, you are in the middle of a letter. Don't start from here. Backtrack. Go back until you find something that starts with 11. And if it starts 110, that is a 2-byte sequence. So you've got 110, and then you've got 10 means this is a continuation. And then the bits in red, that is the number that you read out to tell you what code point this is. If it starts with 1110, it's a 3-byte encoding sequence. If it starts 11110, it's a 4-byte encoding sequence. Now, UTF-8 stops there, because if you go any further, there's no other encoding system you can translate this back and forwards from. But in theory, we could go up to 8-bit encoding sequences, 8-byte encoding sequences, which gives us a lot of headroom for all the alphabets human beings have ever used, all the ones that we're inventing, all the alien civilizations we're going to make contact with, all the fictional writing systems for all the Amazon Prime and Netflix fantasy series that are being commissioned, because we're still inventing languages. Now, you might not think that, but there is a language invented in my lifetime that I bet all of you have used in the last 24 hours. It is the language called emoji, which was invented, this is the original set of emoji. Is invented in Japan in 1998-99 as part of a project, Docomo, which is the big Japanese mobile phone company. They had a thing called iMode, which was traffic information and weather reports sent to your phone handset. And they just wanted little icons to make the thing a little bit friendlier. And this set of emoji is now in the Museum of Modern Art in New York, which I think is quite cool. Within about a year, you couldn't sell a phone in Japan that didn't support emoji because everybody wanted it. And so when Apple launched iPhone in Japan in 2008, it had to support emoji, otherwise no one was going to buy it. Which meant the rest of the world went, hey, if you turn on Japanese keyboard, you can send all these little characters and smiley faces, and emoji just exploded worldwide. And suddenly everyone was using it. Now at this point, there's no standard. Emoji is just this kind of ad hoc thing that mobile phone handset devices are making up as they go along. And people started asking questions. They're like, why, the police officer and the pilot, why are they all little yellow men? I mean, why are they yellow, but why are they men? Why is this? Why can't I find a family emoji that looks like mine? Why is there sushi in the emoji character set, but there are no tacos? Why isn't the flag of Palestine in here? And these kinds of questions, it's a big deal. People want languages which allow them to express who they are and what they care about in a way that's meaningful to them. In 2011, I think, Unicode made a huge step forward. By this point, emoji was part of Unicode. Apple and Google had kind of got together and went, stop fighting for a second, everyone. We get this in a standard so that we don't have to keep playing catch-up with each other, which they did. And they came up with a convention for modifying the skin tone of emoji. And they did this using combining characters. Earlier we saw you can take a C and you can put a tail on it. Well, you can take a thumbs up and you can put medium dark skin tone on it using the same encoding system. And that gives you different skin tones on hands and faces and those kinds of gestures. And now every year, emoji announce a new, or the Unicode consortium announces a new set of emoji that are being added. And we have all of these incredibly rich combinations of professions and ethnicities and genders and, social groups and families and stuff. And they have not sat down and went, we are going to create code points for every one of these. They've used the technology built into the encoding system. If you want to send someone female astronaut, you send them woman, and you send them a thing called a zwidge, which is a zero-width joiner, and you send them rocket. And if your phone handset supports it, it's like, oh yeah, woman plus rocket equals female astronaut. And if you want to send someone an emoji for Mae Jemison, who was a mission specialist on the space shuttle, you can send woman plus dark skin tone plus zero-width joiner plus rocket, and if your handset supports it, it'll draw that. And if it doesn't, it'll just give you those things one after another, and you can figure out what it means. Now, flags. Flags in emoji is really interesting because there are 3 different ways that the Unicode spec says you encode national flags. The flag of Belarus is, there is a set of alphabet letters somewhere way up in the top of the Unicode which are the regional symbol indicators. And if you stick 2 of these together, B plus Y, if your handset supports it, it's like, okay, regional B, regional Y, that's the flag of Belarus. That works for countries. That works for the things which are recognized as countries by the United Nations. If you want to send the flag of England, where we are all standing right now, England is not a country according to the UN because England is part of the United Kingdom of Great Britain and Northern Ireland or something. So you have to send black flag plus. Now, there's a bunch of tags in Unicode that were put in 1994 because someone thought they might be useful later. Then they were taken out in 2010 because no one was using them. And then they were put back in a big hurry when they realized that Apple and Android were using them for the England and the Scotland and the Welsh and the Texas flag, because those are black flag, GBENG is how you send the flag of England. And then there's a handful of other flags in there. If you want to send the pride flag, it's a white flag, a zero-width joiner, and a rainbow. Now, flags are political. If anyone recognize this? This is the flag of the Republic of China. Not the People's Republic of China. This is the flag of the country that is generally known as Taiwan, but formally it is the Republic of China. And the People's Republic of China don't like the Republic of China. And on the Chinese mainland, the thing we think of as China, this flag can get you in a lot of trouble. It is considered a support symbol of Taiwanese independence. Now, this means if you want to sell hardware in China, where they have a lot of people with a lot of money to buy a lot of phones, you have to do that without upsetting the government. So if you go onto your iPhone and you type Taiwan, you get a little emoji pop up. There's the flag of Taiwan. Then go into your settings and change your phone's region to China mainland. And then go back and have another look at your message there. And you'll find that the Taiwanese flag no longer renders, and the key has disappeared from the keyboard. This is what Apple did so that the Chinese government would allow them to sell iPhones and iOS devices in mainland China. Now, Windows, Microsoft Windows, they had the same problem. You can't sell a product in mainland China which has the Taiwanese flag in it, so Windows went, burn the whole thing down, no flags at all. If you go and look at my Twitter profile, if you look at it on the Twitter web interface, it has an EU flag on it. But if you go in to edit that, 1, I want to know how you're editing my Twitter profile, but 2, you just get that. These are the regional symbol indicators, EU. That's all you get on it, because Windows doesn't render any national flags. That's their solution. They're like, no, this is going to get political. We don't want to pick a side, so no flags for anybody, ever. If you want those, you have to use PNGs. There are only 2 flags that work on the Windows operating system. One is the pride flag. The other one is the pirate skull and crossbones. So the only flags you can fly on the good ship Windows are the gay pirate flags, which I'm OK with. You know, if you're going to pick a position statement on this, this is one that I can get behind. Now, my sort of fascination with languages and encoding systems, it started with the pound sign, and then it went through the crash course in Unicode the day we got the Chinese in the event logs. And then I visited Ukraine for the first time to go and speak at a conference there. And I had a blast. I absolutely fell in love with the place. And since then, I've been to Ukraine, I've been to Belarus, I've been to Russia a bunch of times. I started learning a bit of Ukrainian and Russian. And my first trip out there, I had this really weird realization, because I'm walking around Kiev, and I can't read anything. Like, I can't read the Cyrillic Ukrainian alphabet at all. So I can't read the road signs, I can't read the shop signs, I can't read the advertisements, but I can read all of the license plates on all of the cars. And I'm thinking, why in Ukraine do they use English letters on their license plates? This makes no sense. And I went and I looked it up. Now, 1965, the same year as ASCII, there was a thing called the Vienna Convention on Road Traffic. And a whole bunch of countries signed up to this convention, including what was then the Soviet Union. And one of the stipulations of the Vienna Convention is that if you want to drive your car across an international border, you can only use uppercase English, ASCII letters, basically, on the license plates. Now, in 1965, license plates in the Soviet Union looked like this. They were written in the Cyrillic alphabet. And I'm sure at some point somebody went, but what if you need to drive your car out of the Soviet Union? And someone went, comrade, people do not drive cars out of the Soviet Union. And if you really had to, and you could get travel papers, and you could get approval to leave and everything, when you got to the border, they'd give you different license plates. And if you didn't bring them back, you were in a world of trouble. But then when the Soviet Union collapsed in the 90s, all of the new independent states, Ukraine, Belarus, Russia, they all reformed their vehicle registration systems. And today, their license plates look like this. And you can read all the letters on these license plates, right? And the way they did it is they took the Cyrillic alphabet and the Latin alphabet, and they looked for the intersection. What is the overlap? Not the letters, but the shapes that occur in both of those alphabets, and that is the set of characters that is used for vehicle registration plates in most of the former Soviet Union. And if you take those characters and you rearrange them, you get Pike Matchbox. Now, the reason I mention that, next time somebody says to you, I'm going to send you a plain text file, you can turn around to them and go, do you know Pike Matchbox? And if they say, yeah, then you know that they understand about encoding. Big endian, little endian, UTF-32, UTF-8, UTF-16 emoji, the flag of Taiwan, the delete character, code pages, and that they are going to send you a file that probably you're going to be able to open it and make some sense of. And if someone says, I'll send you a plain text file, and you say, do you know about Pike Matchbox? And they go, what's Pike Matchbox? Then hang on to your hat, because you have absolutely no idea what they think plain text is, because as we have seen, there really is no such thing as plain text. Thank you very much. Now then, we are not taking live questions here. If anybody does have questions or got any interesting stories about text that you want to share with any of this, please put them on the Rocket platform. I am going to sign into that in a couple of minutes and go through and answer any questions that have come up. Enjoy the rest of your day. Enjoy the rest of the conference. I'm going to be hanging around out there all day, and then I'm doing another talk to close out at the end of the afternoon, which I'm quite looking forward to. So I hope you'll all, and it's not like there's another talk, so you can go see that or you can go and have a beer. But come see that, we'll all go have a beer afterwards. Sound good? All right. Enjoy, folks. Thank you for watching. Have an awesome day. See you soon.